Audio Jungle. Audio Jungle.
Now, today we have to start that theories of column. Okay, so in theories of column, theories of column. So basically, in column, till now they had asked question like, okay, because we have a different types of the column, so I will explain one by one. But basically, question they had asked directly based on formula in examination. Okay, or one or two times they had asked formula. They had given all four types of the column and four formulas they had given, and they asked which one is the correct and need to match, no, like A and B, like that. And sometimes they ask question also like critical loading and all. So basically we have two types of column. Okay, short column and long column. Short column and long column. So based on this analysis, we have assumption also for the long column. Like short column and long column basically defined with the help of one parameter which is called slenderness ratio. Okay, which is called slenderness ratio. Based on this slenderness ratio, you will find which one is the long column, which one is the short column. That short column basically failed by the crushing load. Okay, and long column will be failed by the buckling load. These are the few things you need to remember. Just like a beam was one horizontal structural member, so similarly that column is the vertical structural member. All right, as you know, that beam was subjected with the transverse load, so that column will be subjected with the axial compressive load. So these are the things, I mean, points you need to remember, and these are basic points, like how to define the columns and all. So now column is a vertical structural member. It's a vertical structural member which carries which carries an axial compressive load. Like if you talk about the beam, so for the beam, I had explained beam is the horizontal structural member, and this beam will be subjected with the transverse load. So this is what transverse load. These are the transverse load P1, P2. This is the horizontal structural member. Okay, that already I had discussed for the beam. So here beam is nothing but horizontal structural member. And what type of load is what subjected this beam is horizontal structural member? It's a transverse load. it's a transverse load. Okay, but what about the column? Here I have written for the column, it's a structural member, but just like a beam is horizontal, so this column is the vertical structural member. Only that's the only difference. Rest everything is what same. Now if it is a vertical structural member, so definitely for the vertical structural member, that load acting to the vertical structural member will be the compressive load. Like how? So I will show you. Suppose this is now vertical structural member. So obviously somewhere you have placed this. No, this member is what somewhere it is placed. So just say this is the vertical structural member. So here somewhere it will be placed vertically. So definitely there will be the compressive load here and at the same time here also. So this is what the compressive load. Compressive axial load. Compressive axial load. Okay. And this is nothing but vertical structural member. At your home, both you had seen, I mean beam and column, both structural member you had seen at your home. Somewhere in structure, maybe there will be column, vertical member will be column, and it will be carrying a compressive load. And at your home itself, if you check ceiling and all, so you will get the beam, which is the horizontal structural member, and over the horizontal structural member, uh, transverse load will be acting over the surface of the beam, right? So this is the difference. I mean column and basically column and beam. Now we are talking about the long column and short column. So two types of column we have. Two types of column we have. Short column. Okay. Now long column is what basically filled by buckling load. Short column will be filled by crushing load. Okay. All right. Now for the long column, it will be filled by the by buckling load, and that buckling load is called as a critical load, which is nothing but PCR. For this PCR we will be finding, okay, PCR for the, because for our topic we need to discuss the long column, not short column. Short column also sometimes called as a strut, that is small structural member. Okay, strut. Short column sometimes also called as a strut. Anyway, so now we have to talk that long column. In our syllabus, in our calculation, we have a long column, so we will focus on long column. So basically this long column will be filled by the buckling load. What is the buckling? I will show you that buckling is the transverse deflection. Okay, buckling is the transverse deflection. I'll show you. Suppose everything we have to do here in very short way. So I will show you. See, this is the vertical long column now we have here, and this is what the compressive load for the column. So definitely, if you this load will be P here, and if you apply the load, then this column will be buckling. It will be buckling like this. Like this. This Y deflection in transverse direction, you can say this is nothing but buckling. This deflection is called as a buckling. Okay, always remember. I'll show you different cases. As I mentioned, this column, long column and short column will be defining with the help of the slenderness ratio. So what is the slenderness ratio? That also we need to discuss. Okay, so if you check here, slenderness ratio, I will write first, then we'll go for the different types better. So what is the slenderness ratio? SLEN slenderness ratio of column. So slenderness ratio, it's a ratio of, slenderness ratio is the ratio of or ratio between the length and least radius of gyration. Ratio of length, I will show you. Ratio of length and least radius of gyration. Okay, means how to get this? If you remember the critical load, okay, this is the derived formula. We need to derive this, but here I am writing here that critical load PCR is equal to, this is the formula we need to derive generally, but here I am not deriving directly, I am writing here. Okay, this is the equivalent length LE square. All right, how you can write this formula? So this formula you can write pi square E, okay, pi square E, instead of I we can write I is equal to AK square. If you heard about the formulation of the radius of gyration, so K is the radius of gyration, so we can write I is equal to AK square, AK square, least means minimum, divided by LE square. What is the I? I is the moment of inertia, okay, is equal to A into K square. Okay, this you should know, where K is radius of gyration. Okay, now, so what is the PCR critical load?
Sir,
Yes.
sir, LE is the least radius of gyration.
No, L is the equivalent length. I will write.
Oh, equivalent.
Uh, LE is equivalent length, or sometimes it is also called effective length. Okay, equivalent length, or sometimes it is called effective length. Here I am writing equivalent length. Okay. Anyway,
Okay.
now, so I'm trying to explain this column in very short way, and whole things I want to mention here because they are asking question very I mean a rare question they are asking from the column. So you should know everything, but we don't waste more and more time for this because it's a big a chapter actually. So PCR is equal to what you have, pi square E I divided by LE square, then pi square E. I is nothing but a k square, k is the radius of gyration, divided by LE equivalent length LE square. We can write this PCR is equal to pi square E into a. What you will get here, it is LE divided by k min square. So it is pi square EA divided by slenderness ratio. I must denote this SR, slenderness ratio, SR square. Check LE by K min. I have given ratio of length and least radius of gyration. So LE is the length, K is the least radius of gyration. So this ratio called as slenderness ratio. Equivalent length and least radius of gyration. And SR is the slenderness ratio. All right. Now I think it is clear. Okay. Now, as I mentioned, that range of the that your long column and short column will be defined with the help of slenderness ratio. So SR, which is nothing but slenderness ratio, it is nothing but LE divided by K min. Okay, so this value will define that column is short or long. So as I told you, that column, two types of column we have: long column and short column. I also told you short column also called as strut. What it is called is strut. Anyway, so if the what it is called slenderness ratio, which is less than 40 or equal to 40, okay, slenderness ratio here, it is less than or equal to 40, then it will be short column or strut. Okay, similarly, if you go for the slenderness ratio for the long column, so that long column slenderness ratio will be SR. Okay, it will be equal to or less, it is nothing but 120. In between it will be the medium column, in between that value will be the medium column. All right, So this is the slenderness ratio. If it is up to 120, you can say up to SR up to 120 will be long column, and SR up to 40 will be called as a short column, or sometimes also called strut. All right. Already I have mentioned here that short column will be filled by the crushing load, okay, and long column will be filled by the uh, uh, buckling load that I already have mentioned. Anyway, now we'll go for the formulation for the column. In short, we'll write the assumption also, then we'll write all the formulation. So basically, for the column, Eilers, okay, the name of the scientist, that calculation for they have given, and that is also called Euler's critical load for long column. Our concentration, as I mentioned, for the long column. So whatever the formula PCRI had shown you, it is the Euler's formula. Okay. Anyway, I will write here. So this is nothing but Euler's critical load. Critical load for long column. All right. Now, so we have assumption. That assumption is important. Okay. Assumption is important for the Euler's critical load for long column. Okay. What is the critical load? Critical load is the load at which the column start buckling, called critical load. Okay, that you should know. The critical load is the load at which the column start buckling. Before that, that column will be a straight column. There is no buckling at all. And what is the buckling? I have shown you, it's a transverse deflection, right? Like for the horizontal, there was the deflection. Similarly, for the vertical structural member also we have a deflection that I already have shown you. Now we'll write the assumption first, one by one. The material behave elastically. The material behaves elastically. Means if you apply load, it will buckle. If you remove load, it will regain its original shape and size. Okay. Number 2, the material is homogeneous and isotropic. Third, the weight of the column is neglected. The weight of column is neglected. Next, the column is perfectly straight and uniform cross section. The column is perfectly straight and uniform cross section. Point 5. The road is perfectly axial. Okay, there is no eccentric loading. The load is perfectly axial. These are the assumptions. Okay. Now, so we are talking about the Euler's critical load. So what is the Euler's critical load we have here? PCR. I can write here Euler's critical load, which is nothing but PCR. This is nothing but pi square EI divided by LE square. EI or E you can say Young modulus or modulus of elasticity. I is the moment of inertia, L is the equivalent length of column. All right, this you need remember. Now moving towards the types of the column with different condition. Now we'll see. Case 1. Okay, we'll write case 1. We have column both end hinged, both ends hinged or pinned. Okay, now suppose this is the column both ends are hinged. If it is hinged, then and the length is what? L. Length of this column is nothing but L. Okay, if you draw this column separately, I can show you. Originally, suppose this is the column, originally this is the column, but if you apply load here P and apply load here P, and remember this is the hinged or pinned, hinged or pinned. So this column will be deflected, and it will be deflected like this. Sorry, should be proper, no? So this is the deflection Y. Okay, and here this length is nothing but equivalent length, which is equal to L only. I will show you that equivalent length will be changing also. Okay, fine. So if you check the formula PCR, so pi square EI by L square formula we have. So basically L is equal to LE in this case. Okay, or you can say equivalent length is nothing but L. If you compare, because your standard equation is what is the your standard equation? Your standard equation is uh, PCR is equal to pi square EI LE square. This is the standard equation. For this pinned case, what will be the PCR? If you derive, you may get pi square EI and length is given L, so L square. Now if you compare this equation and this equation, then what you will get? LE is equal to L you will get. That you need to remember. This is case 1. Now going for the next case, which is called both end fixed. Okay, case 2. Both ends fixed. How it is? Check. Just say this is the column.
Sir, fixed column is also called as clamped, right?
Yes, it is also called clamped.
And sir,
Right.
hinge will be hinge only.
A hinge will also be called pinned. Hinge
Yes.
or pinned. Right. This is the fixed end, or you can say clamped. So, and the length for this of this column is what? L. L. If you calculate the PCR for this, so you will get formula you have. It's a 4 pi square EI divided by L square. Okay. Now if you check this column, because it's fixed column, so this is the fixed end for both. This is the actual condition of the column, but if you apply load here, so this column will be buckling because it's fixed at this end. So this deflection will be like this. Like this. All right. Means we do not have any slope because it's a fixed end. So you will not get the slope at end. Just say this is A, this is B. I will write the condition, but now just say this is the deflection Y. So now if you check what is the equivalent length. So equivalent length, if you compare, this will be the equivalent length LE. How to calculate this? Very simple. You compare with the standard. What is the standard? PCR is equal to pi square EI by LE square. And for this you have a formula which is nothing but 4 pi square EI by L square. So this formula you can also write pi square EI divided by L divided by 2 whole square. Now compare with this LE. So what will be LE? LE will be L by 2. So this value they are asking. Okay, this value they are asking in exam. So what is the equivalent length for the both end fixed? It's a LE is equal to L by 2. This is the column. All right, this is case 2. Now coming to case 3. What is the case 3? Case 3 is the one end fixed, other end is free. One end fixed and other end free. What is the mean of its? Meaning is simple. One end is what fixed, so it will be like this. And another end is what free. Okay. Check. What is the length of this L? What will be the PCR for this? If you calculate. So PCR will be pi square EI divided by 4L square. If you check this, here you have a load P. Now if you check the condition, so this is what fix. This is the actual column. You are applying load P here. So once you apply the load P, then this column will, because it's a free at that end, it's free. So, and it is fixed here at this end, it is fixed. This column deflection will be like this. Okay. P is acting here. Now, because it's a free end, so here you will get the maximum deflection. Okay. Now, standard formula what you have. So if you check the LE, so LE will be what? PCR you have here, pi square EI divided by LE square. Now if you compare this two, so here you can write pi square EI divided by 2L square. So what is the LE? LE is nothing but 2L. Okay. LE is nothing but 2L.
Sir, we can just simply remember all case formula or and LE value.
LE value is very important here.
Okay, sir.
LE
The formula will be same for everyone, just LE will be different.
Yes.
Okay, sir.
No, formula is not same for this. For this case, this is the formula. This is the standard formula. But this formula is what for one in fixed. I just write it. I will explain again later on. First you write one more case it's left. You just complete that, then I will explain. All right.
Sir, I mean to say PCR will be same, just LE will be different, so value will come different for
Right.
every.
Yes. Anyway, now we'll go for the case 4. What is the last case? It is one in fixed, one in fixed and other in pinned or hinged. So we'll make it like this. One end is what hinge, another end is what fix. This is fix. This end is pinned. Length is what? L. For this case, what is the PCR formula? For this case, PCR is 2 pi square EI divided by L square. Now we'll draw the column because this end is what fixed here. So this is fixed and this end is what hinge here. Now if you apply load P here, so that deflection will be like this. Yes. Anyway, for this case, if you check the value of LE, so how to get that? We know PCR is equal to, our standard formula is pi square EI by LE square. Now this is the formula for this case, particular case. So we can write pi square EI divided by L by root 2 square. Because if you square, then again same 2 pi square EI by L square you will get. Now you compare pi square EI in numerator, in denominator it is LE, this is LE square, sorry, and this is L by root 2. So what will be the LE? LE is nothing but L by root 2. This is the value. Now check the all the cases here and try to connect. See here, these are the columns with different given condition. This is what hinge, this is the dot one, dot itself showing this is hinge. Here we have a dot, so this is hinge, this is also hinge. Okay, so definitely if you check for this case, this particular case, this is the formula PCR is equal to pi square EI by L square. But if it is both ends are hinged, then our standard formula, this is the standard formula. Standard formula. Given by Euler's. No? So this is the Euler's critical loading, pi square EI by LE square you have written here. See, this is the Euler's critical loading, here you have written. So this is what is standard formula. But for different cases, different formula you are getting. Like now, first case you are having both ends are hinged. So for this, I told you this is the derivation, but I am not deriving directly, I am writing. So if they have given in the problem both ends are hinged, then this formula you will use. Okay, PCR is equal to pi square EI L square. Fortunately, this formula, I mean critical loading for this particular case and the standard formula both are same. Hence LE will be L. That's the reason you have written here LE is equal to L. This value they are asking in your exam. Okay. So the standard formula is not going to change. Standard formula will be same for all cases, but for all cases this formula is what going to change. So you need to remember this formula for both hinge or pin, then PCR will be pi square EI by L square. Similarly, now suppose we have okay, one more thing I just wanted to tell you. See here, at this end A and at end B. So D, I can say slope, better slope at A and B will not be 0, but this also need to remember. Okay, but deflection at A and B will be 0. Why deflection will be 0? Because it is hinged at A and B. So but slope does not equal to 0. Slope will be there. How you can get the slope? You draw the tangent. If you draw the tangent to this curve, then this will be the slope. Similarly here also, if you draw the tangent to this will be the slope. So you will have a theta, slope, theta is the slope. So slope you will get, but deflection will be 0. Okay, that you need to remember. Similarly here, this is the second case. Both ends are fixed. So this is the standard. I told you standard formula is not going to change. Pi square EI by LE square, yeah. By LE square. This is the standard formula, okay? This is not going to change, standard formula. Standard formula. But for this particular case, when the column is what clamped or fixed at both ends, then this will be the particular formula for this particular case. This you need to remember. If they have given both ends are fixed, then this formula you have to use. Okay?
Sir?
Yes, tell me.
Sir, in all cases, deflection will be 0.
Deflection will be
No, slope will be there, but deflection will be 0.
Not all cases. One case.
Point A and B.
That is true. I mean, here also, if you check, because both ends are fixed, then slope at A and B will be 0, and deflection will also be just like a fixed cantilever beam or any fixed a beam. For that I had explained you that slope will be 0. If you remember, cantilever at fixed end, that slope was 0, if you remember. So here also,
but sir, this will bend, so
no, see, because it is fixed, both ends are fixed at this. So where it is fixed up to certain length, it will be attached. This whatever the elastic line you are getting for the column, it will be attached. Why? Because it is clamped. So for that reason you will not get slope exactly. Okay, I will show you another case. Cantilever.
and sir, deflection will be here also 0.
Deflection will be 0, A and B.
Okay, sir.
See what I am explaining. Suppose this is the cantilever. If you remember, I explained when for the cantilever, when you apply load P here, then what will happen? So this cantilever will bend like this. It will bend like this. So here I had given the boundary condition. If you remember, I said at fixed end, if it is X, so at X is equal to A and B. So at X, A at X is equal to 0, that means point A. So at point A, slope and deflection both will be 0. That I had explained. At X is equal to L, at X is equal to L means you are reaching at point B. So at point B you will get the deflection. You will get the deflection Y. Okay, and at the same time you will get the slope also. But the condition is here, because if deflection will be maximum at the point B, then where deflection is what maximum, slope will also be 0. Okay, if you are talking about the maximum deflection. But the point is, if the ends are fixed, their slope will be 0, like here this cantilever, because it is fixed, hence this will be attached elastic line. This elastic line will be attached elastic line.
Yes, sir, got it.
Remember or not?
Yes, sir, yes, sir. And
yes.
sir, at free point, deflection will be there.
Deflection will be there at free end.
And slope will also be there.
Slope will also be there, yes. But if you are talking about the maximum deflection, so for maximum deflection case, where you will get the maximum deflection? So if you remember that analysis I had given, if deflection is what maximum, then the slope will be 0. Over the elastic curve, tangent line you may get, and that time slope will be 0. Like here,
Yes.
See, this is the maximum deflection case. So if you draw
Yes,
the
yes.
tangent, so tangent will be like this. That means slope is 0. But if you
Yes.
say what is the slope here, so this is not a maximum deflection case. So here you will get the slope. You got my point or not?
Yes, sir, yes, I got it.
So anyway,
So can you go back to case 3?
Case 3. Huh.
Yes, sir.
This point you have written, right?
Yes, sir. I've written.
Now coming to the case 3. So here if you check at point A, at point A, because at point B, this is the point B, and this is the
Slope
point.
and deflection 0
Huh.
at C.
At point B, deflection will be 0. Okay. At point B, slope and deflection will be 0. But at point A, deflection will not be 0. Check, we will get deflection at this point A because it's a free end. Yes or no? And this at this point A, deflection
Yes.
will be maximum, hence slope will be also be 0. Done?
Yes, sir. So maximum deflection means slope is 0.
Yes, yes, yes.
Okay.
I will show you later on. So it will be. Now this is the case 4. This is what fixed, this is what hinge. See, this is hinge, that's the reason this elastic curve is like this. But this is fixed, then this elastic curve is what attached with this. Hope you understood. This is the way to draw for the fixed and for the hinge. So if you check at point B, just say this is point B and this is the point A. So deflection at point A and B will be 0. But what about the slope? Slope at point A does not equal to 0, but slope at point B will be 0. Done?
Yes, sir. Done.
All right. So this is all about the column. So one table I will give to you. Table both ends hinged, both ends fixed, one end fixed, one end free, one end fixed, one end hinged. These are the 4 cases. Types PCR, equivalent length LE. Okay. Now you write all the formula. PCR both ends are fixed, then it's pi square EI by L square. Both ends are fixed for pi square EI divided by L square. One end fixed and another end is what? Free. Then what is the formula? Pi square EI by 4L square. One end fixed, another end is what? Hinge. Then what is the formula? It's what is the equivalent length? For this case, LE is equal to L. What is the LE here? LE is equal to L by 2. What is the LE here? It is 2L. What is the LE here? It is L by root 2. Need to remember this. It's very important. All right. Okay. Problem 1. Okay. The question is a rigid bar GH of length L is supported by a hinge and a spring of stiffness K as shown in figure below. The buckling load PCR for the bar will be, okay. See the diagram. The stiffness they have given for K for this.
The diagram is also given in the question.
Yes, it will be given to you. And this length is nothing but this is the column. What they have mentioned in the problem, option they have given to us 0.5 KL, 0.8 KL, 1.0 KL, 1.5 KL. See, it's very clearly a rigid bar GH. This GH is a rigid bar of length L, and by looking you can see P load is what acting for this column, and it is vertical, so you can understand this is the column supported by a hinge. That's the reason we have this dot here, that hinge support symbol, and a spring of stiffness K as shown in figure. So this is the spring. One end is what supported by the spring, and that spring stiffness is what K. Okay. Now they are saying the buckling load PCR for the bar will be. I mean, if you want to calculate the PCR value for this bar, then how to get that result? That is the question. See, such type of question, if any question based like this they will ask to you, so what you will do, it's simple. First of all, you should know the formulation of the spring. that restoring force is what for the this spring? What is the restoring force? F is equal to K into X. That formula you know. You know this formula? F is equal to Kx for the spring. Have you heard about it?
Yes, sir.
Or what is the X? Can you tell me what is the X? X is the
Uh, Sir, elongation.
elongation or deflection, right? Very
Yes,
good.
sir.
Yes, yes. Elongation or deflection. Now check. See the diagram, and based on this we'll draw the diagram, okay? Because it is hinge at G, so definitely because of the spring elongation at G, this is hinge support, hence this column can move. How it can move, I will show you. See this diagram. So this column will be like this only. Check. If this is the thick support here, I mean for the spring, if because you are applying load P here, so this side we have spring, okay, attachment. If you apply load, then which side it will be buckling? It will be buckling like this side. Yes or no? Why? Because this side we have a spring. You got my point or not there? Tell me. I mean,
Yes, sir.
yes, I mean you can say okay, this side also it can deflect, no problem. If this
It
side
will resist.
then it will compress, and
Yes, sir.
if you saw this side buckling, then this spring will elongate. So most of time elongation will be taken as a positive, so we'll consider this side buckling. Hope you understood my point. Yes or no? Both side, I mean you can take the
Yes, sir.
deflection.
Yes.
This side we have spring. If you show deflection this side, then spring will be compressing, means that if compression will come, then that spring will shorten the length, so deflection will be negative. And if this side column will deflect, then spring will elongate, and you will consider that deflection or deformation is what? Positive. That's the only difference. Rest you can take any side. It's not a condition like only this side. So I'm taking the deflection this side only, so it will be like this. Check. I'm considering this is the spring here, and the column is what? Here, this is the column. Check. This is the actual position of the column, and this is what the hinge support here. But because of this PCR load here acting, so this column will be this is the original condition, but because of this load this column will be buckling, so it will be deflected, and it will be deflected in this way. So now the column is what? Here you can see like this. So, and here the PCR load is what? Acting now. This is the PCR load, and this deflection is nothing but, you can say it is delta. Is that clear to you? Now you can remove this because you are considering PCR you are applying, so this column is what deflected this side, and the deflection is what? Delta we have now. This is what, as usual, the same column is what deflected this side. So what was the numbering? It is G and H. So now this is G, and this column here it is now H. So it is deflected this side. All right. Now, or it's your choice. I mean, you can show in this way. So what is the mean of it? Meaning is very clear. If you take the moment about what? Moment about the hinge support. So here you are considering that deflection you are getting delta, and the spring stiffness is what? K, and what is the force here? Restoring force, it is F. So we can take moment about the hinge support. What is the hinge support? It is G. So we can take moment about taking moment about G. So this PCR into, because you are taking moment about G, so what is this deflection, this perpendicular distance? It's a delta minus you are taking moment about G, so I can say moment about G equal to 0. Summation of moment about G equal to 0. Yes or no? What is the another force? Another force is what? Spring. Because this will give anti-clockwise about G. So what will be the spring condition? Because it is now tensile, so restoring force F will be acting in this direction. Because you are showing that column is what going deflecting this side. Okay, so there will be elongation in spring. So this is what is the restoring force? Restoring force is what? Just opposite to the elongation. So restoring force will be acting in this way. So this F,
Sir,
yes,
sir, this PCR into del will be negative, I guess.
this PCR into del will be negative. Okay, negative. Then this another force you will take positive, because one clockwise, one anti-clockwise. So
So
here,
we have taken
please.
moment at point.
Yes. About G, PCR obviously it will give anti-clockwise, so give negative symbol, no problem. Okay.
Yes, sir.
What about this force F? This force F about uh, G will give the a clockwise moment. Yes or no? Check.
Yes, sir. Yes, sir.
It will
It will be positive.
revolve like this.
Yes, sir.
Yeah.
Yes, sir. Yes, sir. Kx into
So it is F.
L.
It is F into what is the perpendicular distance? It is L. Check the
L.
column length. F into L. Summation of moment about G is equal to 0. Clear? So you got PCR into delta is equal to F into L. Yes or no? What is the F? F is nothing but stiffness K. Here I have written K into X. Or if you have taken deflection delta, then you write delta. K into delta into L. PCR into delta. Check what is the PCR value. This type of problem also they can ask to you in exam. KL. See, this C option is correct. You understood or not here? If you have not understood, ask me. So I will explain once again.
Understood, sir.
Understood, no?
Yes, sir. So can you go back to previous slide, the solution?
Solution.
Yes, sir. Understood.
Right. Now, similarly, many numericals we have. Take any textbook, okay? You solve it. Any textbook you can take and solve. One more question I will solve, then this will be clear to you. See. Problem 2. Now, the rod PQ of length L and with flexural rigidity. Flexural what is the flexural rigidity? EI is hinged at both ends. Both ends for what minimum force F is expected to buckle. Basically they are asking critical load. Option they have given and diagram. I'll draw the diagram first. roller support, pin support here, this is the column pin support at both ends. Okay, now they said this is the force F. In diagram they had given this angle is what, 45 degree. They said what should be the force F is expected to buckle the length of column PQ. It is given L, okay, L length of this column they have given, and it is pinned at or hinged at both ends, and they are saying what force F minimum force required to buckle the column. Okay, they are asking what minimum force required to buckle the column. Option A. Option they have given pi square EI, this is the option they have given to us. We just try to understand simple problem they have given. Actually that column length is what, L, they have clearly mentioned. Okay, now this column is what attached like this. See, the column is what like this. This is the column. Now the thing in this way, the diagram they have given to us. Okay, this is hinged at this end and this is hinged at both ends are hinged. Okay, this problem is here 45 degree. This length of the column they have given L. Now one force they have given to us, this force. Obviously this force is required. Why? Because this is what, roller support. If this force is not there, then it will roll that side. Actually here it is hinged, no problem. So now they are asking what should be the F. What will be the F minimum force? I think they said. What is the minimum force? No? What minimum force required? F minimum. What F minimum should required to buckle the column is, PCR. Now that PCR value they are asking to us. Okay. So now how to proceed this? So we have F, not F min. F min is PCR, but F they have given to us. How to proceed this problem? So this is point P here, check, and this is what, point Q. We need to solve this problem. So how to proceed this? Simple, we will take this column, and for the column what type of load is there, check the theory. Load should be the axial load for the column. I mean, if this is the column hinge support at both ends, so this load should be like this. Yes or no? We have hinge support here, and orientation you can change, no problem, but the condition is load should be axial. check this F is axial loading. No, it's not axial loading. It's not axial loading. So you need to convert this force into axial loading. So see this F they are asking to us. This is what F. This angle here it is given how much? 45 degree. So what will be this angle? This will also be 45 degree. So what will be this axial loading? It will be F sine 45, or you say cos 45 because angle is making with this. So you can say, because sine and cos both will be same, because one for this F one component will be here, another component will be here. So this side angle we can say this is cos 45. Okay. So now axial loading you have calculated here. So this is F cos 45. So definitely this will also be F cos 45. Now you got this. Okay. Now, so what is the minimum loading required? So this F minimum will be what? F cos 45 is equal to PCR. That's all. What is the PCR for the both in hinged? It is pi square EI by L square. Now you just solve it. What is the F min? It's nothing but pi square EI by L square cos 45. So F min is nothing but cos 45 is 1 by root 2, I think. So it will be root 2 pi square EI divided by L square. This is your answer. Check option B. This is your answer. Yes or no? Done?
Yes, sir, done.